Student friends and physics loving people, I'm back again with another video on wave particle duality. This is the second part of this particular topic, wave particle duality. In the last video we have shown how the de Broglie relation is responsible for matter wave and how it can take account of matter wave. In this particular video we will derive the de Broglie relation and find its expression for different cases, for both non-relativistic and relativistic cases. So this actually led to Nobel Prize for Louis de Broglie in 1929, and actually this was according to Einstein, there are only 2 steps away from him to get the Nobel Prize. In a funny language, he showed that for a photon of frequency nu and rest mass m0 which is equal to 0, the relativistic momentum is p and mass is m, the energy is given by equal to h nu, and also the relation from E square equal to m0 square c to the power 4 plus p square c square, with m0 is equal to 0, it becomes p square c square, and ultimately p is equal to E by c. With equation 1 and 2 you can see that p equal to h nu by c, and since nu by c is equal to 1 by lambda, so ultimately p is equal to h by lambda. This is what is de Broglie relation. So with only just 2 steps, in a very easiest way, we can derive the de Broglie relation, and which however needs some to be on a or a more generalized way that we need to derive it. So let's take care of this equation in terms of some relativistic point of view in a more general sense. So since the material particle is represented by wave function, so whose periodic variation gives the matter wave, so we take psi as the wave function which undergoes periodic changes, and at a particular time t0 and at the space x0, y0 and z0, we represent that particular wave function as given by equation 3, where this psi naught is actually representing amplitude of the wave function. And now this nu naught is the frequency that is observed by the observer at rest with respect to the particle. So here the naught present as a subscript is actually representing the condition that the observer is at rest. Now let the particle is given some velocity. Now according to relativistic point of view or transformation equations, the time can be written like this: t naught equal to t minus bx by c square, square root of 1 minus b square by c square, as given by 4 through Lorentz transformation equation. So putting 4 back in equation 3, we get psi equal to psi naught sine 2 s pi nu naught t minus bx by c square, square root of 1 minus b square by c square, as given by equation 5. Now let's compare this equation 5 with equation 6, which is the general equation of a wave motion. The general equation of a wave motion is this: y equal to a sine 2 pi nu t minus x by vp, where this nu is the frequency, t is time, and then vp is the phase velocity of the wave. So comparing 5 and 6, we see that vp equal to c square by v and nu equal to nu naught by square root of 1 minus b square by c square. So this particular nu is representing a frequency when that particle is having some velocity, and this nu naught is representing frequency when the observer is at rest, and this is the frequency when the observer is in motion. So with this 7 and 8 obtained from the comparison between 5 and 6, we can now see how that Einstein mass energy relation can be helpful for further improvement of this equation. So E equal to h nu naught equal to m naught c square. This is simply Einstein mass energy relation. So nu naught equal to m naught c square, and from 8 and 10 we now can say that nu equal to m naught c square by h square root of 1 minus b square by c square. Now m naught by square root of 1 minus b square by c square is a relativistic mass, so it is equal to m. So nu is equal to mc square by h, as given by equation 11. And as we said that m is the relativistic mass, as given by equation 12. So nu is now from equation 8 is transformed to equation 11 now. with this equation 7 and 11 here, this is equation 7 Vp and this is 11. Putting them together, we get lambda equal to Vp by nu, and this is nothing but it's equal to since Vp equal to c square by v and nu is equal to mc square by h, and ultimately we get lambda equal to h by mv, which is the famous de Boer relation. So we see from equation 13 that your wave nature is related with particle nature, which is contained in the momentum part of this particular equation, and the wave nature is related with lambda, that's wavelength of the equation. So it's a very simple kind of thing, starting from relativistic variation of time and then frequency, and using this equation 7, 8 and then 11, we get this equation of lambda. We also note that in 13 there are two velocities here involved. The one velocity is related with mechanical motion, and that is the particle velocity, and there is another velocity Vv which is associated with propagation of the wave or the propagation of the phase of the wave, and is known as phase velocity of the wave. And the relation between V and Vp are as given by equation 7. So thus we have derived the de Boer relation in a simple way, considering relativistic point of view. Now coming back to equation 13, we can designate this quantity in terms of both non-relativistic and relativistic point of view, where this momentum can be both relativistic as well as non-relativistic. So since we see here that this in 13 this m is relativistic mass, which with a factor gamma, whose gamma is nothing 1 by square root of 1 minus b square by c square. So that's given by equation 14. The relation for the de Boer relation for a relativistic case can be written like this, where this r is representing simply the relativistic case, and this pr is representing relativistic momentum. And if you see here that since m is equal to gamma m naught, so our h by mv is now transforms into h by gamma m naught v, and so thus the equation 15 represents the relativistic wavelength, de Boer wavelength. And on the other hand, for a non-relativistic case, this gamma is equal to 1, because in a non-relativistic case, as from equation 14, v is very less than c. In that case, this quantity will be negligible as compared to 1, and gamma is equal to 1, and so the relation is h by m naught v, and since m naught v is simply the non-relativistic momentum, so this equation 16 is representing non-relativistic wavelength, de Boer wavelength, and where this p and r is the non-relativistic momentum. So both the de Boer relation can be put both in relativistic form as well as in non-relativistic form also. And also one more modification that you can bring into equation 16 is that this p and r, that non-relativistic momentum, can be written like this, and which is obtained from this relation E equal to p square by twice m naught kinetic energy. So this lambda nr can be written like this, h by square root of twice m naught E. So this is also another relation that can be used for non-relativistic de Boer wavelength. And the difference between relativistic and non-relativistic de Boer wavelength is that here only this gamma is equal to 1 for non-relativistic case, and gamma is greater than 1 for relativistic case. This is the only difference between equation 15 and 16. So next we can have another modification for equation 16 by putting by considering a particle in an electric field where the kinetic energy is nothing but the potential energy EV, where V is the potential difference, and in that case lambda nr is equal to h by square root of twice m naught E square root of twice m naught EV, as given by equation 18. And for thermal motion, the kinetic energy is given by this particular thing kBt. Kb is Boltzmann constant, T is temperature, and again instead of E we will write here h by square root of twice m naught kBt, equation 19. So for any kind of situation, we can represent the de Boer wavelength from this basic relation 17, where it relates de Boer wavelength with energy. And with all this, we are left with some assessment. And the first question is that if radiation can exhibit particle nature, then so also particle can exhibit wave nature. This is simply the Bohr's justification for matter wave. Then what is matter wave? Is it like a water wave? What is matter wave means that it's a wave of probability. So since it's a wave of probability, so it cannot be like a water wave. And what is de Boer relation? Just simply we have just get it. What is the significance? It relates the particle nature with wave nature. Derive the de Boer relation and express both of its relativistic and non-relativistic form. That's what we have done just in the last slides here. And then lastly, why is the wave nature not observed in daily life? And this is a question that you must answer, that we should mean that you are understanding. And this answer will be particularly in terms of the value of the de Boer wavelength. So with all this, I am ending up this video. Thank you very much for watching the video. Keep watching our videos and never forget to comment on our videos. Thanks once more.